Hello, everyone. Glad to welcome all of you to the already traditional and now mega popular Young Members Group webinars. Today, if I'm not mistaken, we are performing our 7th webinar. Lucky number, I think. Leading of this webinar is me, Vlad Shekhovtsov from Ukraine, and Nikola Tosic, already from Spain. Today's topic sounds very intriguing. I must say, even globally, worldwide topic. Modeling efficient strategy for modeling punching failure of a flat slabs, which presents my colleague from Switzerland, from the very head of the FIB, Andri Setiawan. But before I officially introduce today's speaker, and he will start his session, I will tell you about our activities. I think you already heard about FIB, the International Federation of Structural Concrete. It is a worldwide organization uniting professionals in the field of concrete and reinforced concrete structures, particularly from all over the world. But you might have a question: if I'm young and strong, how can I be a part of this community? The answer is Young Members Group. So what are we doing? The FIB Young Members Group represents a platform for dialogue between young professionals, encouraging the creation of National Young Members Group, involving young people in the FIB commissions and task groups, making and maintaining contacts and networking, organizing regular meetings, events, and conferences for young members. Also, we organize the Best Paper Award competition during all FIB symposiums. If you want to be a part of our community, feel free to contact us in any way suitable for you. We maintain our Facebook page, so don't be shy, subscribe, like, and also you can visit our section of the official FIB website. So feel free to contact us. You can also use our direct mailing. Before I start, just few technical details about the webinar. The webinar will be recorded and shared on the FIB social channels. Only the panelists are able to speak during the webinar. You can use the chat function where you can post where do you come from and general feedbacks, not questions about the webinar. So you can start till now, just chat, just type where you're from. It's very interesting and important for us. Also, you can see near the chat button, use the question and answer form, bottom of your screen, to post questions for the speakers, and we will answer to all of them at the end of the webinar. Please do it. Don't hesitate to ask any questions. It's very interesting when we have hot discussion after the presentation. And one's new frequently asked feature of our webinars is certificates of participation. Participation in a webinar is completely free of charge, but those persons who want to get a certificate, you must contact publication FIB International. You see email on your screen, and to ask for your certificate. The fee for such certificate will be 10 Swiss francs. It's about 10 Swiss francs, about 10 years. We can smoothly move on to what has united on this brilliant evening. And now the brief information about our hero, about our speaker, Andri Setiawan. Now he's postdoctoral research fellow in Lausanne, Switzerland, in EPFL. He got his PhD in structural engineering at Imperial College of London, United Kingdom. He is involved in FIP. He is International Young Members Group Board, chair of FIB Indonesia Young Members Group. Also, he is a member of Action Group 8, Commission to Analyze and Design. His research interests is punching shear, shear in slabs and beams, and numerical modeling. Oh, sorry. The agenda of our webinar, but I think Andri could start, so I can give control to Andri and he tell everything he wants. I stop my screen, sharing my screen. So please, Andri, I'm switching off and you're king of the show now.
Good afternoon, everyone. First of all, let me kindly introduce myself. My name is Andri Setiawan, and now I'm a postdoctoral research fellow at EPFL Switzerland. Before I start my presentation, let me thank David Fernandez Ordonez as the FIB Secretary General, and also Corinne and Marie from FIB Secretariat, who was helping me to organize this event. And I would also thank Vlad and Nicola, who are helping me today as the panels. So I would start sharing my presentation now. The title of the presentation, as Vlad has already mentioned, it's Efficient Strategy for Modeling Punching Failure of Flat Slabs. And for today's webinar, I divided the section into several parts. So in the first part, I'm going to present about the research background in a very general way, and then research aim, which is the objective of this research. And then we are moving on to the state of the art about the punching shear itself and also about the numerical modeling in general. And then in the fourth part, we are going to move on into the main part or the main contribution of my research, which is related to the proposed modeling strategy. And I also divide them into like two parts. The first one is the implementation and verification. And the second part will be about the extension of the model to deal with several practical design scenarios. And lastly, about the conclusion and future work. So I just want to let you know that the background and research aim, I would take some minutes to cover everything, because I designed the presentation and the slides to serve as a general information for general audience who are not familiar with either punching or with the numerical modeling. So I will spend some minutes there. So for the research background, I'm going to start with what is flat slab buildings and what is punching shear phenomenon. You can see in the screen, flat slab building is a structural system where you have the floor slabs directly supported by the columns without the presence of beams or girders. So this kind of structural system is widely used in Europe, especially in the countries with low seismicity risk, because it offers many practical advantages, including minimizing the floor-to-floor height, because you do not need to have the beams. So you can reduce the floor-to-floor height, so you end up with more floors with the same height. And also, without the presence of the beam, you can make a simpler reinforcement installment, which also speed up the construction process. And also, with this system, it gives more freedom for the architect to be able to lay out the building. And lastly, of course, faster construction time. However, without the presence of beams or girders, the load from the slab is directly transferred to the column, and it may cause a concentration of bending moment, and also shear stress around the column region. So one of the key aspects which typically governs the design of flat slab structure is what is called a punching failure, where we can see a diagonal crack propagating within the concrete strut, and it disturbs the shear transfer mechanism between the slab and the column. And in the worst case scenario, where we can find in most typical older flat slab buildings where we do not have this continuous bottom reinforcement, we can have what is called progressive collapse, where the slab is fully punched through the column, and it is a very dangerous failure mode because it happens in a very brittle manner, and it doesn't give any time for the occupants to evacuate from the building. So we have seen from some previous incidents, like the one that is like very well known is the failure of Sampung department store in South Korea in 1995. And it was like a full collapse. And another thing is happening in Northridge during the Northridge earthquake in 1994 in California. This is the picture of Bullock's department store, which was partially collapsed during earthquakes. So moving on, we are going to discuss a little bit about the current code of practice and what kind of, let's say, simplification and assumption that design codes are typically used. So first of all, before discussing the codes, I'm going to explain about the typical test setup that we do in the lab in order to study or to investigate punching. So if you see the one that I point here, this is the configuration of actual continuous flat slab system, where you have the hogging moment, or we call it like negative bending moment around the column region. And also we have a positive sagging moment. However, in order to test these full scale slabs in the lab will be very expensive and it will take a lot of space. So what most researchers do in the past was they try to cut the slabs, so they only investigate the slabs in the hogging moment region. So what they do, they cut the slabs within the border of the contraflexure line, so that we have a slab like this, which is we call it as isolated slab mostly, so that we can have like a smaller scale specimen. So this is, for example, a typical slab test that were done many times at the PFL. Just to give you an idea, the dimension of the slab is around like 3 meter by 3 meter, and the thickness is around 250 millimeters. So this typical isolated slab represents an actual slab with a span of around 6.5 to 7 meter. And in typical codes of practice, they also derive their formulation mostly based on this isolated situation. So what we use in practice is that we have the column in here. And for example, for Eurocode, we have a control perimeter located at 2D away from the column. And what we do is that we calculate the resistance along this control perimeter, and we check that resistance with the shear stress calculated along the same perimeter. For Eurocode 2, there are 3 parameters that we consider: the concrete strength, the reinforcement ratio, and the size effect. And it was fully empirical. For SEI, it is similar, but the control section is somewhat like closer to the column. It is 0.5D, and it is only governed by the concrete strength. And it's also empirical. And for model code, which is written by the FIB, it's similar to SEI. It assumes the control perimeter to be at 0.5D from the column, but it is mechanically based, or let's say rational model, which consider many parameters like concrete strength, yield strength of the rebars, reinforcement ratio, size effect, slenderness, and aggregate size. I will discuss the derivation of the model code, which is employed in my model, in more detail later. But what I want to emphasize from this slide is that this approach of having a control perimeter is very, let's say, practical and easy to implement for design practice. And mostly we can say that this gives quite a satisfactory results. It's relatively conservative and easy to implement. And it mostly used for designing new structures. But however, sometimes we need more than just conservative or safe. We want to be more accurate. For example, when we assess existing flat slab buildings that need to be strengthened, or for example, when the owners wants to like have a change of use in the building, we need to be accurate. We need to be more exact when predicting the punching capacity. So in these typical isolated slabs, we neglect many contributions in real slabs that is actually contributing more to the punching resistance. So I'm going to discuss a bit about major parameters or major contributive items that were neglected when deriving this isolated situation. So yeah, the first one is about moment redistribution. We know that in reality, we are having positive moment as well in the midspan. And this positive moment is not captured in the typical test with isolated slabs. So this will also contribute to increase the punching resistance. The second thing is about compressive membrane action. So imagine that when the inner part of the slab inside the hogging region starts having cracking and yielding of the bars, the slab would expand laterally, whereas the outer part of the slab is still not fully cracked, for example. So the outer part would provide like a natural confinement to the inner part of the slab, which actually increases the resistance. It is similar like having like a natural pre-stress to the inner region. So this is also not explicitly considered in the design codes, for example. And the third aspect is the shear distribution. In most design codes, we assume that punching happens when the maximum shear stress is reached. But in reality, for example, this is a very nice study by Sagaseta et al. Showing that when you have slabs with different reinforcement arrangement or slabs that was like loaded in a one-way fashion, not in two-way, you can see in here that the maximum rotation and minimum rotation is not the same. So for example, if you load the slabs in this direction, you will have the maximum rotation to be higher in this part and then lower in this part. So you can have more resistance in the side where you have minimum rotation. So this is also contributing to the increase of punching resistance. Last thing is about the post-punching resistance. We know that when the slabs is fully punched, the remaining resistance is contributed by the integrity reinforcement, which is basically the reinforcement that are installed continuously through the bottom region of the slab. And it will activate what is called like tensile membrane action, or you maybe call it as a catenary action. And this will help the failed connection to regain. You can see in this test, after punching, due to the activation of the integrity reinforcement, we can achieve somewhat resistance that is close even to the pre-punching resistance. And this is very beneficial and very important when we are having, you know, like a progressive collapse scenario. We can prevent the spread of the progressive collapse by having this tensile membrane action, for example. So all of these factors are not explicitly considered in design codes, and we want this all to be considered when we are assessing real flat slab buildings. And we know that using analytical approach is somehow limited. We cannot really consider everything in here. So people or researchers or engineers, they usually resort to numerical approach. So in the next part, I'm going to show you the numerical approach that people are usually used to model punching. So in general, we can divide the modeling into two parts: the 3D solid modeling approach in the left, and then the 2D shell modeling approach on the right. So for the 3D solid modeling approach, the advantages is that we have realistic stress state everywhere out of plane and in plane. And we can have accurate representation of forces redistribution, both moment redistribution and also shear redistribution. And we can also model the post-punching explicitly by modeling the bar as like, say, like a solid element within the slab. However, there are several disadvantages as well, because you need to mask the solid elements through the thickness. We end up with a large number of elements, large number of degree of freedom to solve. So we are really inefficient in terms of computation time. And that makes this approach is mostly suitable only for sub-assemblages or for a small portion of the building. And lastly, the failure criterion is, of course, a little bit more complex than 2D shell because you consider the interaction in the three-dimensional problem. For the 2D shell modeling approach, we assume that the out-of-plane stress is negligible, so that we can only model the slabs as like a XY plane only. So it's like just like a paper, basically. And then the advantages of the shell modeling approach is that because of the rotational degree of freedom that it has on its node, we can have less number of elements. We do not really need to discretize through the thickness of the slab, so we can have more efficient computation time at the end. And because of the first reason also, this 2D shell is more suitable for large structure. For example, if you want to model the whole building, this 2D shell is still possible, whereas if you use 3D solid, it will be a nightmare for sure. And for the 2D shell, it's also relatively simpler to the failure criterion. However, a typical classic 2D shell, because we neglect the out-of-plane stress, of course, it cannot really capture punching, because punching is a, let's say, a 3D failure mode. The secondly is that also because of the first reason, we cannot model shear distribution, and post-punching states cannot be also modeled explicitly. So in my research, we are trying to, let's say, improve the performance of the 2D shell modeling approach so that we can try to, like overcome these disadvantages. So we can end up with a model that is efficient, but also sufficiently accurate to simulate punching as 3D solid. That's the big dream at the time. So the research aim, we are planning to develop an efficient modeling strategy to simulate punching failure. And the keyword is that is suitable to analyze large structure. And of course, we can only do this by modifying the 2D shell. But the model that we want must also be able to, the first thing, I put an underline and bold there. It should be able to accurately represent the transition from elastic, cracking, punching, and post-punching stage. It must also be able to realistically capture the presence of shear distribution that is happening in reality. And it should, because we want to use this model for actual continuous slabs, of course, the model that we develop needs to be able to take into account flexural continuity and compressive membrane action. And lastly, of course, it needs to be numerically robust, so we can ensure a numerical convergence. That's the research aim, the big dream of that time. So for the state of the art, I'm going to review a bit about, let's say, previous attempts of previous studies who are trying to modify the 2D shell. So of course, I'm not the first one in this topic. There are many researchers have done this before. So I will try to categorize the strategy that people have employed before me in order to modify the 2D shell element. The first category is the simplest one, which is the post-processing, which means that you just use the nonlinear shell analysis to produce the load rotation response without any shear failure, and then you intersect with the failure criterion. For example, this one, the study from Belletti et al. And Xu et al., they used the failure criterion of critical shear crack in order to detect the failure. So basically, you can see the intersection between the failure criterion and the curve is the failure point. So that's the simplest one, which is by post-processing. The second thing, which I called as internal modification, is done by modifying the out-of-plane constitutive behavior. So instead of having elastic out-of-plane shear response, you modify it so that you can consider nonlinearity as it does in 3D solid. So this was done by a study by Pollack and also Herenick and Vecchio, where they modified the out-of-plane response of the slab. And the last category, I call it as the external modification, because we do not do anything to the shell, but we put additional elements. We call it connector elements. So you can see in here that the slab is modeled just as a normal slab, but then you put a connector element around the punching perimeter so that the punching failure is triggered locally by that connector elements. But this approach by Keivani and Liu has some limitation, I would say, at that time, because they do not consider shear distribution. So they trigger the failure as soon as the first connector fails. The second thing is that the shear capacity of the connectors was predefined before the analysis, for example. So you cannot really consider how membrane action changes the resistance and so on. The third thing is the post-punching capacity was not explicitly modeled. So we think that, okay, we can start doing something like external modification, as was done by Keivani and Liu, but we want to, let's say, provide an alternative of their shortcomings. And the first question at that time was what failure criterion to employ when we use connector element. The prediction of our model is solely governed by the accuracy of the failure criterion. So we need to, let's say, be careful when we select the failure criterion to apply in our model. So the next slide will be discussing about a brief, like let's say, overview about many different failure criterion that are available. So analytical approach to predict punching. Just for the sake of completeness, I'm going to show you like all the categories. We have the flexural capacity model. We have the plasticity-based model, which models concrete as a plastic element with a reduced concrete compressive strength, effective compressive strength. We also have fracture mechanics model. And the last one, we have what is called kinematic model. And for kinematic model, we also have two derivations, which is the strain-based model and critical shear crack theory. So after reviewing all these models, we based on three different criteria. The first one is, of course, the accuracy. We want to have a failure criterion that is accurate. The second one is the versatility. We want to have the model that can be used for slabs with shear reinforcement, without shear reinforcement, or with fibers or with a pre-stress force, for example. And the last one is the model needs to be compatible with finite element. So I will let you know later what it means by the compatible with the finite element. But at the end, we decided to employ the critical shear crack theory by Professor Muttoni. And in the next slide, I'm going to give you like a very brief review about the critical shear crack theory. So the critical shear crack theory assumes a sector element like this. If you see the slab from the plan, you can see the slab is divided into like a slices of slab, like a slices of pizza, for example. And then each slices are separated by the radial crack. And the kinematic assumes that the inner part of the slab behaves like a spear. Basically, you have constant tangential and radial curvature in here inside the region. And then for the outer part, it behaves like a conical, which means that the radial curvature here is 0. It moves like a rigid body, basically. And it only has tangential curvature, for example. And this theory assumes that the transfer mechanism, the load transfer mechanism, transferring the load from the slab to the column is disturbed by the presence of the diagonal cracks that is propagating inside the concrete strut. And the ability of these two crack surfaces to transfer the shear from the slab to the column is governed by the crack opening, the width of the crack, and also the roughness of the crack, because you need to activate aggregate interlock in between. For the crack width, it is assumed that the width of the crack can be approximated as a function of the flexural deformation. This is a very nice model because you are coupling both flexural behavior and also shear, because the bending rotation is mostly flexural. So we can say that when you have larger rotation due to the bending behavior, you also have less resistance because you have wider crack opening. And this is the full equation for the model, but we can see in the graph, the y-axis is the resistance and the x-axis is the crack opening normalized by the roughness of the surface. We can see that as the crack opening grows wider in the x-axis, we have less resistance, which is very physical. So the model can be used by just intersecting the load rotation with the failure criterion, as I have shown you earlier. So for example, this is the shear force, you have the slab rotation, we have the failure criterion, and then we have the load rotation. And in this case, for example, we can capture the first scenario of failure where punching occurs after full yielding, punching occurs after partial yielding, the intersection is the failure point, and the last one is the third case, punching occurs without yielding. So as I said before, the model couples the flexural and also shear. So we do not really need to like separate those two. We do not really need to check whether it's a flexural mechanism or is like a pure punching or anything. We can combine both in this formulation. And the derivation, it's a long derivation, but I'm just going to give you like an idea. The critical shear crack theory assumes like two major things. The first one is the crack geometry and the crack kinematics. And the second thing is the shear transfer mechanism and the constitutive that governs its transfer mechanism. So we see in here the critical region where we have punching. This blue region is the discrete crack, which is basically crack that occurs above the neutral axis. And in here, we have the contribution of aggregate interlock from this part, and also the contribution of residual tensile strength. I call it contribution 1 and contribution 2. And then in the compression zone, we have shear carried by the concrete compression zone. I call it contribution 3. And the last thing, we also have contribution from the doubling of the flexural bars. So for a certain crack opening, you know the crack displacement and crack sliding, you can calculate the contribution of each, and then you integrate them along the crack, assume crack surface, you get resistance. So you do this for the next crack opening, and then you get the failure criterion. So basically, the punching resistance is simply the integration or the total of each contribution along the critical shear crack. So for those of you who are interested, you can refer to Simoes et al. Studies, which completely describes about this derivation. So now we are moving on to the proposed modeling strategy that I have, which is basically the main idea is combining the, let's say, the advantages of shell element, which is efficient, and also the failure criterion from the critical shear crack. So we call it, as it is, we call it a joint shell punching model, which is basically combining joint and shell. So the idea is that we have the shell to tackle the bending behavior, whereas the joint will take care of the punching failure. So if we see the plan view of the slab in here, I'm going to show you this is the plan view. We also imaginary cut the slabs into several sector elements, which we can be seen here. We have imaginary sector elements. And the edge representing the slab edge for isolated slabs or contraflexure for continuous slabs. And we, as I said before, we use shell elements to model the bending behavior. And then at a certain location close to the column, which in this case, we are assuming that the punching happens at the half of effective depth from the column to be consistent with the critical shear crack theory, we put joint elements. So the joint elements will trigger the failure around this perimeter. So as you can see from the name, this is combining joint and shell. So for the shell, you can typically use any shell formulation. It doesn't really matter which like constitutive model or anything that you use, but the most important thing is that you need to have a model that can be able to capture rotation accurately, because the critical shear crack theory assumes that the resistance is directly governed by the rotation. So the accuracy is dictated by how accurate your shell on capturing the rotation. So for example, in this work, I'm using the shell formulation proposed by Izzuddin et al. So we are using the Reisner Minlin shell type, where the plane sections remain plane after deformation, but not necessarily normal to the mid-surface of the slab. We consider the shear deformation. And we are using the layered approach, where we discretize the shell into several layers through the thickness. And we model the reinforcement as a smeared approach, as a layer with an equivalent thickness, basically. And we also have a concrete biaxial model to consider the interaction of compressive and tensile and shear in plane direction. So for the second part is where the novelty comes from, which is the joint formulation. The joint itself is, I would say, quite unique. The joint is consisting of 4 nodes. So you can see, sorry, in the figure, you have node 1 and 2, node 3, and node 4. I will explain to you one by one what is the function of each node. So this joint has 6 degrees of freedom, 3 translation, and 3 rotation. We assume that all the other 5 degrees of freedom, except the out-of-plane shears, are rigid. So we ensure a compatibility of the shell itself. But for the out-of-plane, we impose a certain constitutive behavior in order to be able to capture punching. So it's like, let's say it's a 1 degree of freedom joint spring at the end. So let me go back to the picture. I hope you can see my pointer here. This is the position of the first and the second nodes. So at undeformed configuration, the first and the second nodes are coincided. So when the punching happens, it will separate to each other. They will separate to each other, and it simulates the breaking of the concrete. So now you probably ask, like, why you need to have node 3 and node 4. So node 3 is actually it's not a structural node. It's like an imaginary monitoring node. So for example, I put node 3 along the contraflexure in here, if you see, and also node 4, I put it in the axis of the column. So you can see node 3 is in the contraflexure and node 4 is in the column. Why? Because I use node 3 to inform about the absolute slab rotation on each step, whereas node 4 is to monitor the column chord rotation. If we subtract the rotation that I got from node 3 and node 4, we can get the relative slab column rotation, which is used by the critical shear crack theory to calculate the resistance. So the idea is that every load step, these two nodes, node 3 and node 4, will monitor and save the rotation, and then I can subtract them internally in the algorithm in order to check the remaining resistance that I have at that current step, and then I can determine whether the punching has occurred or not. So it's an iterative scheme. And also, node 3 and node 4 are required to do a transformation of the global rotation, because in finite element, the rotation that we cap normally is rotation in the global direction in X and Y. But in this scenario, we need to transform that into a radial rotation, which is basically the rotation that controls the opening of the tangential crack. So we need also those two nodes to transform the rotation. So the algorithm, I'm not going to show you like any complicated or any sophisticated like script or anything. It's just a very simple schematic drawing, basically. Yeah. So the algorithm has three major components, as any different algorithm. It has the subroutine input, and then the decision-making process, and the last one is the subroutine output. In the subroutine input, we are trying to store some data from the main analysis program to the subroutine, and then in the subroutine output, we are trying to give back the results from the subroutine to the main analysis. So for the subroutine input, there are three different inputs: the calibrated parameters, the critical shear crack theory parameters that are used to produce the criterion, and also the most important one is the monitored parameter, which is basically in here is the rotation at previous step, the shear at previous step. By comparing these two, we can see whether failure has happened or not, and also the displacement, so that we can calculate the stiffness on each step. So we are going to start. The first if in the decision-making process is that if the joint shear is less than the critical shear crack criterion, this means that punching has not occurred yet. What happened is I'm just assuming an elastic behavior. You can see in the left bottom side of the slides, we have a linear response like that, simply linear response without anything. Now, the second stage is that, okay, the shear force in the joint has already larger than the critical shear crack, so you have failure. But now we need to ask to the joint element, is the failure happened on all joints or only at one joint? Why do we need this? Because we want to consider shear distribution. And shear distribution happens when one of the joint fails and then some of the joints have not failed yet. So for example, if we found out that failure only occurs at one joint, we say that, okay, this is not a global failure, this is just a local failure. Let's go to the redistribution stage. At this stage, you can see in the figure, the resistance is no longer increasing, but it is decreasing following the shape of the critical shear crack theory curve. So for the joint that has failed, the resistance will reduce, whereas at the same time, the shear will redistribute to adjacent joints where the failure criterion has not been intersected. So that's the idea of how we can simulate the redistribution. So now, if all joints have failed, so the shear redistribution have completely done, all the joints have exhausted, we trigger the transition of the global punching to the post-punching stage. So now the question is the remaining resistance is still larger than the post-punching resistance? If it's yes, then we are having a, sorry, if it's still larger, we have a drop. We have a drop from the global to the post-punching resistance. And then finally, we have a plateau, which is representing the contribution from the integrity reinforcement. So by having the constitutive behavior that consists of stage 1, stage 2, stage 3, A and B, we are trying to simulate all the important milestones of the punching phenomenon in slabs. So this is the physical illustration. Just before punching, you can still see that the slabs are intact between the inner and the outer part in here. They are still intact. But then just after punching, if we zoom into this region, we see that the red dots and the yellow dots are actually representing the first and the second nodes that are started to separate because of the punching failure has triggered there. So this is how the model will simulate the physical failure here. So now we are trying to implement this algorithm into finite element framework. And we are using an in-house structural analysis software from Imperial College London. It is called ADAPTIC. So we wrote the subroutine and then we implement the subroutine in this program. So this is the typical EPFL test, and I just cut the slabs into a quarter by utilizing the symmetry condition. So we have the line of symmetry in here. We have the support model as restraint, and then as I said before, at a predefined control perimeter, we have joint elements distributed uniformly there. So we apply the point note in here. So we are using quadrilateral element and smeared approach for the reinforcement, and the element size typically is around 50 by 50. This size is a little bit finer than usually what people use in shell, but yes, because we need to have several joint elements along this control perimeter. So actually the element size is dictated by like how many joint elements that we want to have in here. Because if you want to simulate redistribution, it is better to have like more joint elements. And for the benchmark, we also do some analysis in a commercial finite element software. It's called Athena from Cervenka Consulting. This is the same slabs model in 3D solid elements. We have the line of symmetry. We have the support model as 3D elastic steel plate. And we also mask the slab through the thickness by 10 elements, which gives quite sufficiently accurate bending behavior and also the point note and the loading plates. So you can see we use the linear hexahedral element, linear order, I mean, and then linear order tetrahedral element for steel plate. And also the reinforcement is modeled as a 1D truss element. And the element size is around 25 by 25 by 25, around this region where the shear stress is governing. So now we are moving on to the initial verification that I did with this model. I divided into the screen into 4 parts because I'm going to have like 4 different cases in here. The first case is we are going to test this model for a concentric punching test with the large, with a deep slab. And this was the, I think was the largest slab that was tested at the PFL, with a dimension of 6 meter by 6 meter by 500 millimeter thick. So we can see in the graph here, the black curve is the test, and also the red test curve is the model that we developed. So we can see that the load rotation response is captured nicely, and also the occurrence of punching. Of course, because of the failure criterion that we employ already consider size effect, we are able to capture the punching of these large slabs accurately. In the second scenario, we are trying to investigate the ability of this model to capture the post punching. So this was also the test from EPFL, from Fernandez Ruiz et al. 2013. So we can see in here in the right that we are not only capturing the punching load accurately, but also the post punching resistance quite nicely, I would say. In the third scenario, we are trying to simulate some slabs with compressive membrane action, so that we can, let's say, validate whether this model is capable of simulating continuous slabs or not. This test was done by University of Nevada, and they have a lateral restraining frame structures in order to prevent the slabs to expand laterally when it cracks. So we can have like a lateral stiffening effect. So we can see in here, for both slabs with a lateral restraining system, we are capable of capturing the load rotation and also the failure load quite accurately. The last one is the slab with a flexural continuity. So this is quite a unique test setup where we have an isolated slabs, but we have a steel frame system which introduces a sagging moment. So instead of only hogging moment region, with this typical test setup, you also have a sagging moment along the edge. So we are testing these 2 slabs with different reinforcement proportion in the midspan and in the end span, and we are able to capture both scenarios accurately, both the load rotation and also the failure, which means that we are capturing the moment redistribution accurately in the model. So for the test of the last test that we do is to be able to capture shear redistribution. To show this, we are going to use a static case from slab PT34 of Sagazeta, which was loaded in one-way bending. So this is the slab, the quarter of the slab. It has the same reinforcement arrangement in X and Y, but it was only loaded in the Y-axis in this loading point, if you see in the screen. So we can imagine that for these joint elements in here, this will be weaker because the rotation in this part will be less, the rotation will be higher, which means that the resistance will be less. Whereas in the yellow part of the joint, we have smaller rotation there, which means that the shear resistance will be higher. So with this study case, we want to show how shear force can redistribute from the red dots to the yellow dots. Okay, so this is the results. We are trying to, let's say, relate what happens in the global behavior and also what happens in the local behavior of the joint. So in the figure in the left, we are seeing the global behavior of the slab. We have the shear force in the y-axis and then slab maximum rotation in the x-axis. So for the first stage, we are loading the slab until 75% of the predicted failure load. And now we are investigating the response of the local behavior of the joint at the same level of load. And the first part is the joint at the weak axis, located at the center line, which is basically at the symmetric line. So you can see in here, this is the joint force and this is the slab maximum rotation. The joint force increases in here until around 15 kilonewton. And then in the next figure is the variation of joint force along the weak axis. So for example, this joint actually represents this part, represents only one dot in here. And the other dots are representing the joint force at different joint along that axis. So we are going to do the same for the strong axis. First figure here showing the local joint force at the center line at the single position. We can see the increase in here. And also in the second figure in the right, it's the variation of joint along that axis. So it's a compilation of different joint, 1, 2, 3, 4, 5, 6. There are 6 joints in here. This part represents just a single dot in here. So I'm going to show you what happens of the evolution between the global and local. At 85%, we still have an increase, a normal increase in here, and also in the strong axis, it is still like a normal situation. Also to 95%, we have a higher increase in here. But now the most interesting part happens between the 95% to the 100% of the failure load. We see we have a flatter response in here, which indicates like a typical shear failure at the end. But now we can see in the weak axis, the joint force has softened. So this part has failed locally. So we can see in the right figure, the red dashed line is actually lower than the yellow dashed line, which means that all of the joints here already in the softening part. And we are expecting the joint in the strong axis to take over the forces. And yes, it does. So the joint at the strong axis will take care of the load that is redistributed from the weak axis. And we can see in here nicely that the joint at the center line, which has the smaller rotation, at the end of the failure load will have the highest portion of the force because the resistance there was highest at the end. So we are showing with this illustration about the evolution between joint forces and the global behavior, which satisfied our objective to consider shear distribution. So yeah, we see the softening in here, the arrow you see, and also the increase of joint force at the strong axis, and also a complete redistribution in here. So now for the extension of the model, I'm going to really briefly discuss about the extension of the model. We did 3 different extensions of the model. The first extension is to deal with slabs that are supported on rectangular or walls, rectangular column, like long columns and walls. The second extension is to deal with slabs subjected to eccentricity, with monotonic and cyclic eccentricity. And the last one is to deal with the slabs with shear reinforcement. So I'm going to present them in like each extension in one slide. So for the extension of the slabs for slabs supported on columns and walls, the difference is that when you starting having a rectangular or long column, the shear stress becomes less and less uniform. So you can see in here, the left figure, it's a typical scenario where the C is the column size and D is the effective depth of the slab, and they are equal. This is representing a uniform stress that is typically modeled in the previous stage of the verification. And we are moving to the right part where we have a larger square column or having an elongated column, where you can see that the shear stress concentrates more on the corner region and a minimum shear is carried by the middle region. This is a very typical situation that we found in practice. For example, if you have a partition wall and also a core wall where you have a slabs directly supported by the core wall. So we can see that there are a region with a concentrated two-way shear and also a region with a minimum one-way shear. This happens in both scenarios. You have two-way shear around the corner and one-way shear along the outer part of the region. So what we do in here is that we are going to distinguish the contribution of the two-way shear in the punching region and the one-way shear in the outer part region. But we don't know at the time, like, what is the border? How can we define a border separating the one-way shear and two-way shear? So we did some comprehensive solid analysis, 3D solid analysis. I'm modeling a slabs like this with a rectangular column from the real test, and we extract the variation of shear forces along this control perimeter. We have 4 regions, the shorter side and diagonal, where we expect higher shear stress, and we also have the longer side and the discounted region. The 1.5D that we define in here is compatible with the model code suggestion that if you have very long column, you need to neglect this region so that when you consider the resistance of the punching, you only consider the 1.5D from the column. So we try to use this assumption, and actually it matches quite well with the actual distribution. We can see that the majority of the load is carried by the longer side, diagonal, and shorter side, and only the minority of the forces is carried by the discounted region. When we do the integration, okay, sorry, this is showing here, yeah? So the dot in here representing the line of symmetry in here, and then this one represents the shorter side. So when we integrate the force, we found out that 90% of the load are carried by this, let's say, two-way region, and only the minimum shear is observed elsewhere. So we did modify the model by 2 assumptions. We assume that we only put punching joints along the corner, and then we treat the resistance of the one-way shear with a minimum shear resistance with a rigid plastic joint. So this is just a very brief and short overview of the extension that we did. So for the extension 2, for the slabs with unbalanced moment, the situation is also different. We see here, this is the slab tested at TPFL as well. With a monotonic eccentricity, you can see that the eccentricity goes to the right of the column. So you can see the tangential crack actually only forms on one side. We did some 3D solid analysis as well to confirm that. Yes, we can see that the principal strain, the maximum principal strain, which is tension, is concentrated only in the hogging region, where the shear stress from the unbalanced moment is adding the shear stress from the gravity load. So in this scenario, we cannot really redistribute the shear to the whole control perimeter because it's not physically realistic. So we need to make an adjustment on to what extent we are allowing the joint to redistribute. So this is what we do in a very brief way. This is a sector elements. We have hogging half here and then sagging half here, or positive and negative. And eccentricity is going to this way. You can expect the shear stress is higher here. So what we do is that when we have a monotonic loading, we assume that the redistribution can only happen along the half of the slab, which is only along the hogging half. So when the last joint at the slab center line fails, we assume that, okay, redistribution is done, because otherwise it will continue to redistribute to the sagging half, and in reality it won't happen because you need to have a very ductile slabs in order to be able to redistribute to the sagging half, and it doesn't make sense. For the cyclic one, because we know that with the repetitive loading of cyclic, we have a plastic accumulation of rebar strain, the crack width will be higher. So the redistribution physically will be less. So what we did is that we are limiting the, basically we assume no redistribution at all. So when the first joint at this part, at this red hatch region fails, we assume that, okay, the connection has failed. So this is how we distinguish the behavior of monotonic and cyclic of the slab. So yeah, we did some simulation. You can see the black curve represents the test, the blue curve represents the prediction from Athena 3D solid, and the red test curve is the prediction of the joint model, which is quite accurate, I would say. And another interesting thing about the joint model is that instead of only just predicting the load rotation, we can also quantify the contribution of each transfer mechanism. For example, if you have slabs loaded in unbalanced situation, you can carry the moment by eccentric shear, by torsion, and also by flexure. So by having joint elements, we can quantify that. which can be seen here. So we have the contribution of the eccentric shear, we can have the contribution of the torsion side face and the flexural front face. That's also like one of the benefits of having this model. So lastly, for the slab switch shear reinforcement, we consider two different scenarios. The first mode of failure is when you have the critical shear crack intersecting the shear reinforced region, and the behavior is more controlled by the yielding or the straining of the shear reinforcement. So we have this criterion already from the critical shear crack theory, so we can just add the contribution of shear reinforcement as a function of the rotation. So this is pretty much simple, to be honest, because the model is already been available. So the second mode of failure is that when you have a large diameter of shear reinforcement with a narrow spacing, so the crack is not going to propagate into the shear reinforced zone. Instead, the failure will be happening by the crushing of concrete at the inner face of the slab. In this scenario, we also have the criterion, which is basically a function of the detailing and the anchorage condition of the reinforcement, the spacing, and also the concrete strength. So we do this, we do the modeling. For the first one is the test isolated slabs reinforced with headed studs. We model two different slabs. The first slab is PL11 with a lower reinforcement ratio, 0.23%. And as we can see in here, the black curve is the test, the dotted gray is the Athena, and then the red curve is the model that we have from our proposed model. So we can see in here that the criterion cutting this failure is the inner, which is basically the first mode of failure. So this is consistent with the saw cut of after the slabs, after the test, where we see the crack is cutting the shear reinforced region. And for the second scenario, we have the PL7, where the reinforcement ratio is 4 times higher. So in this case, the failure is governed by the crushing of the concrete. So interestingly, with this failure criterion, we are not only able to capture the punching capacity, but also the correct failure mode. And the last test that we did was a continuous slab tested by Chana and Desai. It's quite an old test from UK, where they use one leg stirrups. And this represents like a slab supported by the contraflexure region. So you have some continuity in here. You have positive moment. So we can see that the red test curve is the prediction and the black curve is the test results. So we can see that the prediction is also quite well and accurate. So just to conclude, we are doing all the validation. This is the summary of the accuracy and the variation of the prediction. I'm going to present you the mean and the coefficient of variation of the joint shell punching model that we did. You can see in the graph in here, the y-axis is the measure divided the predicted capacity. It will be equal to 1 if it's exactly the same as the test. For the original JSPM, which is the initial verification, we did 33 specimens with average of 1.033 and variation of 9.4%. The second scenario is with large long support area. We simulated 24 specimens with the average of 1.025 and variation of 8.6%. And the slabs with unbalanced moment, both with monotonic and cyclic, we simulated 21 specimens. The average is 0.977 and the variation is 8.3%. And lastly, for the slabs with shear reinforcement, continuous and isolated, we simulated 12 specimens with average of 1.006 and variation of 7.3%. So we are really satisfied with the model because the average is very close to 1 and the variation is less than 10%. And most importantly, we are also comparing the required computation time that we had for the same slabs between our model and also the 3D solid, just to make a distinct comparison. For the joint shell punching model, for a typical slabs, we only have 961 nodes, whereas for the slam slabs, where we model using the Athena 3D solid, we are ended up with 23,785 nodes. And this is the required computation time, 265 seconds, which is basically like 4 minutes or something like that. Yes, and Athena solid, of course, it has more nodes and degree of freedom, so it takes almost like 100 times longer to finish the simulation. So to conclude, we are developing an efficient modeling strategy. We call it joint shell punching model, which is the main idea is combining the use of 2D shell and also nonlinear joint elements. And we have sufficiently proved that JSPM capture the elastic cracking, punching, and post-punching stage reasonably well. And we can also take into account the shear distribution, flexural continuity, and CMA. And We have also extended the model so that it can handle the punching of slabs with elongated columns and walls, slabs with unbalanced moment, monotonic and cyclic, and slabs with shear reinforcement. So we have let's say, covered many practical design scenarios. And lastly, in the previous slide, we also have confirmed about the accuracy of the model and also the variation, which is very nice. And of course, the most important thing, because there is an efficient word that we are putting there. Yes, we proved that the model is more efficient and it requires significantly less computation time than the 3D solid analysis. So the goal is to be able to use this model to analyze a full-scale building in a more efficient way. So that's all. Thank you very much for your kind attention. I want to acknowledge both of my supervisors and my collaborator from Imperial College London, Professor Robert Volum, Dr. Lorenzo Maccorini, and Professor Basam Izzuddin. And I also want to acknowledge the sponsor of my PhD from Indonesian government. Thank you very much. And if you have any questions, please do ask. But if we don't have enough time, please you can freely contact me using the email address shown here, or you can also connect with me in LinkedIn or ResearchGate so that you can discuss with me or send any questions or any things that you want to ask from this discussion. Okay, thank you very much. And yeah, I'm looking forward for the question and answer session. Thank you.
Thank you, Henry. I must just say, wow. Before I will read you a question, you have a lot of questions, I think. So, where are the questions? I ask you one question from me. What are the problems that you haven't solved yet? Could you number it?
Yes.
Because you have solved a lot of problems. My PhD was at 2011, and I will defend it. And for that time, some of the problems you have they haven't solved. But now I see the answer and the result that these problems are has an answer. So what is the problem still haven't solved? Still solved?
Yeah. Okay. Thank you very much for the question, Vlad. Just to let you know that all the validations that I did during my PhD was mainly for internal columns. So now one of my colleague at Imperial College is continuing my work. Now she's doing the extension of the joint shell punching model for edge column and also corner column, because we found out that the behavior of the edge column and corner column is different with internal columns. You have eccentricity, so you have more complex interaction between the shear and bending moment there, and also some torsion of the side edge of the column. So I think the next issue will be how to address how to extend this model for edge connection in general, and at the end to simulate a full structure. So a full structure which of course has internal edge and corner column all together in one building. For example, for doing progressive collapse analysis or something like that. That will be the big long goal, I would say.
Okay, I see. What are physical mechanical characteristics of concrete you need to know to perform your model? Only characteristical of strength or some deformation characteristic?
Yes. Okay, thank you. I think I have said it in a very brief way during my presentation that the methodology that we develop in here means to be a general methodology. So it doesn't really need to be exactly the same approach as we did for the shell. But the idea is that you need to have the shell elements that is able to accurately simulate the bending behavior. Bending behavior can be also affected by membrane force. For example, if you have a compressive force in plane and also a tensile in plane force, for example, it will affect the curvature, and at the end it will affect the bending behavior. So the shell model that needs to be combined with the joint needs to be able to capture at least the rotation accurately. For the out of plane deformation, I mean, you can just have elastic behavior because at the end, the shear failure is not triggered by the shell, but externally by the joint. And for the joint to work accurately, it needs to have a correct input of the state of rotation. So it's the shell, the function of the shell itself is more to provide a correct kinematic for the joint, I would say, something like that.
Okay, thank you. So let's start to ask you questions about our attendance. The first one from Andri. What is the recommendation of the R value of flat slab structure?
Yes, for the audience who are probably from Europe that might be not familiar with the R value, it's called Q value in Eurocode 8. It's similar to behavior factor. Basically, it's a factor that you apply to reduce the elastic spectrum to your plastic spectrum in design. It's a good question. In Europe and in America in general, when you use flat slab, you can only use it as a secondary lateral resisting system, which means that you need to have another system. It can be in a form of a shear wall structure or in a form of brace structure, a structure with bracing. So the R value will be employed depending on the primary structures, but for the flat slab itself, you need to check the compatibility of the drift. So for example, in SEI, you have a special section that you need to do to check whether for a certain design drift, whether punching failure happen or not. It's a function of the gravity shear ratio and also the drift. So the R value does not really apply for the flat slab itself, but it applies for the primary structures. But during the analysis, you need to check the compatibility of the drift between the primary and the secondary structures in order to check whether punching has happened or not, something like that. So the R value can follow the primary structures.
Okay, I see. The next question is from Adele Sphere about AC code. For example, in AC code, reduce negative moment. I think it is a question about AC code.
I'm not sure. Wait, probably it's a statement, I think.
It is a statement, okay. It's a statement about the continuous about your previous answer. If not, Adele can to share another questions that we can understand and answer it. The next question from Albert Hansel: using the kinematic approach for predicting punching shear demand, it seems that the material stiffness degradation at not linear phase up to cracking occurs gives less significant effect to the punching shear behavior. Thus, it means that if we have a slab, for example, a slab made from steel, it will produce the same behavior as a reinforced concrete slab. Can you elaborate more about this approach? It's about physical mechanical.
Yes, it's a good question. So yeah, the initial elastic stiffness was actually representing the out of plane shear deformation before the critical shear crack propagates. So in reality, the opening, or let's say the stiffness, would be very high because critical shear crack is not like a flexure. It opens in a very abrupt manner. So it's basically like having a very large stiffness, and then when the shear crack starts to open, it has like a plateau like that. So yes, it doesn't really affect the prediction of the punching behavior, but in my model, the inclination of the joint element, I call it K-ing. I think, yeah, I call it K-ing. It was calibrated based on a situation with unbalanced movement. So why? Because when you have unbalanced movement, in the model, you have a moment and then it will be distributed through three different mechanisms, as I said earlier: eccentric shear, torsion, and flexural. So if you have a very steep K-ing, the shear component will be very stiff. So what happens is that more of proportion of the unbalanced moment will be carried by the eccentric shear and will be less for the torsion and flexural. What happens is that punching failure will be triggered very early. On the other way around, if we have a very shallow inclination of the stiffness, what happens is that most of the unbalanced moment will be carried just by flexural and torsion. So in my case, I would say that the K-ing is more like a calibrated parameter based on a situation with unbalanced moment. But for a situation with a concentric without any eccentricity, it wouldn't affect the prediction, because at the end, you will always have redistribution. And when you enter to the redistribution stage, the behavior is solely controlled by the rotation. So I would say that the first part doesn't really affect anything for concentric scenario.
Okay, thank you. The next question from Guillermo Diaz. Can I obtain the Drakatos 2016 reference? What is the name of the paper?
Yes, I mean, you can, I don't know, like you can search it at Muttoni PFL. They have the library of the paper there, and you can just search the author Ioannis Drakatos, and you can find the reference there. Actually, it's all complete there in the website at the PFL.
Okay.
Both the thesis and also the journal paper, so you can access both for free.
Okay, thank you. The next question from him is internal slab-column connections under monotonic and cyclic imposed rotations. It is a question.
Yes.
Is it imposed rotation?
Yes, it's imposed rotation. So the gravity shear is actually constant. So you only introduce eccentricity. So it's a situation that you have under, let's say, an earthquake, for example. So the shear force is constant. So it's imposed rotation, yes.
Okay. The next questions from Albert Hansel. How about the presence of the drop panel? Can the model predict the patching shear behavior also?
Yes, it's also a good thing. Yes, you can do this. I imagine that you need to put two different control perimeter. The first control perimeter is located inside the drop panel with the capacity calculated based on the full depth of the drop panel. And then you need to have another control panel outside, you need to have another control perimeter outside of the drop panel, which only represents the original thickness of the slab. So it's similar like having a slab switch reinforcement that fails outside. So you can simulate this by having a two perimeter with two different layers of joint, for sure.
Okay, the next question is from my colleague from Ukraine, Igor Yakovenko. He has also the model of the concrete. The question is, what parameters do the width of opening most dangerous cracks determine? I think you understand how you can determine the width of the crack, of the shear crack. I think is it constantly for all the length or not?
Yeah, I'm not really understand the question, but yes, the opening, what parameters do the width opening most dangerous cracks determine? Yes, so I mean the opening of the crack in this model is affected by the bending behavior is already like coupling the shear and also flexural deformation. So for a given rotation, you have both sliding and also opening. So yeah, I mean the kinematic itself, I'm not really sure, to be honest, to answer this question. Like basically in the model, I'm just talking about the model. The model of critical shear crack theory simply assumes that the resistance is governed by a single critical shear crack, which means that in reality, of course, you can have several cracks. You have several crack coalesced to one crack. But in this model, we simplify that we have like a one critical shear crack that is developed at the end, which governs the failure. And we assume that these cracks will like transfer the force through the aggregate interlock and the compression zone and everything. And all the resistance is governed, let's say, by the kinematics of the single crack, something like that. I hope that answer. I'm not really sure, to be honest.
Maybe on also answered about the value of these crack openings.
The largest crack opening within a reinforced concrete joint.
Can we about this question? Can we get from your model the width of the crack opening on the different stages of?
Yes, I mean we can actually, if we represent, let's say the relative displacement between the joint is like a shear deformation. But to be honest, I haven't really validated whether it is really makes sense comparing to the real shear deformation, because in reality, you can have a stable growth of critical shear crack only if you have shear reinforcement. If you don't have shear reinforcement, basically the shear crack will just open and then it suddenly like grows like crazy. And it's really hard to really monitor the development of shear crack gradually, I would say. But in the model, yes, we represent the opening of the shear crack by a relative displacement between the joint elements. That's what we can do, at least.
But have you some limits for width of this crack? 1 millimeter or
Yes,
0.5?
yes, that's a very good question. Actually, the model that I did is, each joint, they don't talk to each other. So for example, if one joint fails, the other joint, they don't know whether my friend has already failed or not, something like that. I don't have any master joints, basically, which can check each joint has failed or not. So what we do at that time is to trigger the transition between the the global failure where all the joint has exhausted to the post-punching stage. We assume a threshold of displacement of 1 millimeter in order to make sure that at that level of displacement, I have ensured that all the joints has entered the failure stage, something like that. So yes, as you said, I assume a threshold of 1 millimeter in the model.
1 millimeter. Well done, Andri. The next was statement. I think in the future, perhaps Andri can also explore patching failure mechanism of cast-in-place flat slabs that utilize post-tension tendons. What about post-tension tendons?
Yes, thank you for the question. Yes, actually, I have explored this, but in a simple way. So there was a very nice test campaign by Thibaut Clement from EPFL. He studied the influence of post-tension and also compressive membrane force externally and also a rotational restraint externally. And I would say that the critical shear crack theory is also able to, let's say, capturing those phenomena. So I would say that, yeah, I mean, the model is ready because if you have post-tension, the difference is that you will have a smaller curvature because of the compressive force. So you can capture the shell because the shell element itself consider the interaction between the in-plane membrane force and also the bending behavior. So of course, with the compressive force, you have a smaller crack opening or smaller rotation, which resulting in a larger shear resistance. So yeah, it can be done for sure with the same model.
Okay, and continue his question. And flat slabs that have hollow core in them, hollow core slabs?
Yes, for hollow core slabs, we haven't really investigated that, but I'm not sure. But I think even if you use voided slabs, from what I know is that around the punching perimeter regions, you don't put a hollow there. So the behavior of I mean, there is a reduction of strength, of course, but I mean, it's still under research, to be honest. Voided slabs, they are still doing some tests right now. But from what I know is that you don't put the slabs, you don't put the void everywhere, especially around the column. You usually put a solid slabs there. So the behavior will be somewhat similar to the typical solid slab, but of course you have some reduction because of the voided outside of the control perimeter. But yes, we haven't really investigated that. Probably it's going to be a nice topic of research in the future. Yes.
Okay. Next questions. In order to modify to this slab analysis, do we also need to include the large displacement assumption in order to catch the slab behavior correctly?
It really depends on the magnitude of displacement and rotation that you have compared to the, let's say, the thickness of the slab, for example, something like that. But from the model that I have, the model that I use in ADAPTIC already considers the nonlinear geometry of the slab, but I honestly do not know how much is the effect of considering nonlinear geometry or not. Probably it's also a nice thing to check in the future, but yeah, it really depends on the thickness of the slab, the stiffness of the slab, and how large is the displacement. Because in reality, if you have slabs without shear reinforcement, the rotation of the slab when punching occurs is relatively small. So I would say that nonlinear geometry wouldn't affect that much. But if you have, let's say, slab with shear reinforcement, where you may achieve large deformation, probably in that scenario, then the nonlinear geometry will become more important, I would say.
And to continue these questions, when you compare your model with experimental results, it's
Yes.
my question.
Okay.
About have you compared the displacement of the slab or only stresses?
That's good. Very good question. Deformation is more tricky, to be honest, to capture, because at large, I mean, when you close to failure, with the increase of small force, you may have a large shear deformation, especially when you deal with slab switch shear reinforcement. So I would say that the prediction is better for the force. It's a little bit worse for the deformation, especially if you have a complicated, let's say, a loading scenario, for example, the one with the imposed rotation, cyclic, and so on. I would say that the displacement is not entirely captured, because if you have cyclic, you grow the crack for every step, and we do not really capture that in the model. So probably the displacement will be less accurate. Yes, but so yeah, in the meantime, what we really check, as you see in the last slide of my presentation, was mainly the force, the strength, the relative strength between the prediction and the test. But yes, the model can also, let's say, capture the deformation, because as I said before, this is like a kinematic model. So, I mean, you can intersect after the yielding or before the yielding or without yielding at all. So yeah, it should be able to handle everything.
I have another questions to continue our.
I think there was some questions where they asked for the slides. I don't know.
Well, in the meantime, you are receiving really a lot of congratulations.
Thank you for thank you everyone for
a really great
congratulating.
presentation.
And then we have hot brainstorming discussion.
Which is nice. I mean, I really appreciate the discussion here. Yes.
I have one more question. I'm waiting for my time again. Okay. So my question was about your layers of your 2D element. I think it is not the common plate finite element plate. Plate. It is I think it is layer element. Yeah.
Yeah. It's yes.
And what kind of layers? What kinds of layers it consists? Yes. And what about reinforcement? How we model reinforcement in your layer element?
Yes. Thank you very much, Vlad. So yeah, the shell itself, it's called nonlinear layered shells. Basically, the difference between this shell and conventional shell is that you discretize the shell into several layers, and each layer represents a plane stress element, where you have 2 by 2 gauge points on each layer. And to get the moment and shear and axial and everything, you basically integrate the stress from each gauge point on each layer through the thickness to get the external force, to get the moment and also the shear and everything. So each layer is like a plane stress elements with 2 by 2 gauge points. And
yeah. I understand, Andri, it's without sigma z.
Yes, the out of plane stress is assumed to be negligible. Yes.
But what is the layer of the reinforcement? Is only reinforced ratio or
no? It's modeled as an equivalent plate with equivalent thickness. So, for example, if you have a diameter 16 by 100 millimeter, you can calculate the equivalent thickness by just dividing the area with the spacing. So you get like a thin steel plate there in between the layers. So you model the reinforcement as an individual layer, as a steel plate with equivalent thickness.
Okay, understand. And can we model when we have only one layer of reinforcement?
Yes.
Yes.
Yes, you can. Yeah, but it's smeared approach. So, for example, if you have different spacing of reinforcement, you need to have different cross-section properties for that, because it's not a discrete one. So, for example, if you have different spacing of reinforcement, they need to be classified as 2 different section properties.
Okay, I understand. So what about the questions? We are looking for slide 17, but
there is no question, or there is a question?
No, we have a question. We have 2 questions. So, from Arif is for slide 8 and 70. Are these punching failure on slab without round column only?
No.
About...
No, mostly are with a square column. It's combined, square column and also a round column, but I think mostly are square column. But all of them are isolated slabs, isolated internal slabs without shear reinforcement.
Okay, and the next questions is big questions. Would you consider using higher patching capacities for your failure criterion when checking for failure under height strain rate loading? Essentially modifying the 0.75 multiplier in the failure criteria. So this should not change anything from the model. Also, in the initial response is assumed to be linear elastic. Do you think this is a valid simplification? Why not use a nonlinear relationship, as this could intersect the failure criterion at a lower load and a larger rotation? A good question.
Yes,
please
very
answer.
good. Yeah.
Please answer.
Yeah, thank you very much, Carl, for the question. Yeah, for the first question, to be honest, I'm not really expert into that, into the high strain rate on impact loading, but I would say that in order to be able to capture that phenomenon, then yes, we need to do something. We need to modify the failure criterion in the model. And I'm not sure, but if the impact load also affects how the slab behaves, I mean, in terms of the shell behavior, so we need also to modify, let's say, the properties of the concrete, for example, to consider the high strain rate effect or something like that. But yeah, I mean, the model that we do, giving the results that is predictable, you know what I mean? Like, we modify something there and they will produce the results that are expected. So it really depends. Yeah, if we change the failure criterion only for the high strain rate, yeah, basically it doesn't change the load rotation, but it probably just become like less, for example, or higher basically. And for the second question, yes, it's very it's a simplification, as I explained earlier. In reality, you have some nonlinearity there as well, and as you said, it might affect the failure criterion at different load, but this is particularly true if you have a local failure. I mean, for a scenario where you have a complete failure along the control perimeter, at the end, everything will be governed only by the rotation. So no matter, let's say, the corner joint will fail earlier, but still the final global failure will be governed by the last joint, which is basically at the level of rotation at that time. All the other joints will have resistance equal to the rotation at that time. So it will affect the intersection of the first joint, but it will not affect the failure of the last, because as I said, at the end, after the redistribution stage, the resistance of all joints will be dictated solely by the rotation. But yes, if you have a local failure, like when you have a rectangular column or a wall, where you have the punching happens locally without fully redistribute to elsewhere, yes, it will affect. If you have a higher, let's say, a very rigid stiffness, then the shear stress will be higher, so it will fail earlier, for example. So you can affect the failure based on how you treat the initial stiffness. So it's a subject for further study as well, how to refine this initial part, especially when you are dealing with a localized failure where you don't have a complete shear distribution, something like that. But thank you very much for the input and question.
Okay, Andri, thank you. Could you show us the slide with your email, please? Because
yes.
Because we have we must end our hot session, and if anyone want to ask something, Andri, privately, you can ask for directly by email or LinkedIn. So thank you everyone who was attended to the webinar. Don't forget about our Facebook page. Look for these and previous videos of our webinars on YouTube, on the official FAB channel. Please subscribe, like, and follow us. Follow FAB Young Member Group International other events. We have still two webinars in next 2 months. So please register it.
Do you want to show the screen plot for the next webinar? Because you have it in the slide, right? I think the date and everything.
Yes. So the next webinars are for 4th of November and 3rd of December. It's very hot topics, so please register on the official LinkedIn channel of the FIB website. It's the events part of the site. And about certificate, if you want to get certificate for from this webinar, please contact publications and to ask for your certificate. Thank you, everyone. Thank you, Andri, for your great work.
Thank you, Vlad. Thank you, Nicola. Thank you, David.
I really appreciate, really liked your research work. It's very done and hard work. And wish everyone to be healthy, active, and see you at the next Young Members Group webinars. It will be even cooler. So thank you very much.
Thank you, everyone, for coming as well.
Bye.
Thank you.